Hey guys, this is part 3 of the AWR interpretation section. So in the last two videos I would have just given a brief highlight of all the sections in AWR report. So this particular AWR set of AWR videos is specifically related to resource manager, CPU quantum. Okay, but also I would have explained in generic terms as well, not specific to this weight event. In the last video, in the part 2, I stopped at IO stats. So let us continue with the IO stats. So just hit a like and subscribe for more AWR related videos. So yeah, coming to the IO stats. So this is very important section whenever our issues related to IO. Okay, so why any database would be having an IO issue, right? So there are multiple reasons. So the storage subsystem, the storage arrays won't respond in a given amount of workload, right? So obviously we know the saturation, CPU saturation. So likewise for IO also we will be having saturation. So if the devices, if you are sending requests to the devices, right, the storage devices, and if the devices are 100% utilized, right, so if you are giving load more than that the storage system can take, during those cases obviously the storage controller will not be able to it will be under some contention, like it will be having some overhead, and it will be difficult for the storage arrays to respond, right? Obviously the disk, the SSD or any storage that you use will become heat, and obviously at the hardware level, if it becomes heat, even at the software level you will be seeing some issues. Okay, this is not only the case, but there are a lot of different scenarios. So sometimes the IO subsystem will be fast, but from the database layer the configuration settings may not be proper, or from the database layer there may be some delays. Okay, so if the CPU is not sufficient, then also there will be some issues, right? So obviously both CPU and IO response should be good. If the session is waiting on CPU, then also that session has to do some IO as well parallelly, right? So if the session is waiting on both CPU and IO, then that would become a problem, right? So we already know that a session either uses CPU or it will wait on something. So when the session is utilizing more CPU, at the same time it also requests more data from the IO subsystem, then there will be double contention, right? Obviously when we are using parallel feature, both CPU and IO will become a contention, because when you use parallel there will be checkpoints, because even at the storage, the segment layer, there will be segment level checkpoints. Okay, so when you are using direct reads, direct path operations, so obviously when you are using parallel option, there will be direct path load or direct path reads, so which may cause further frequent checkpoints, right? And obviously when checkpoints are more, DBWR also will write the dirty buffers to the data file. There will be a lot of IOs. So yeah, either the IO issue will be from the database end, DB end, or it will be at the IO subsystem, the storage or the operating system end. So we need to isolate where exactly the issue is. right? So to get an idea on the database perspective, these all sections will help you in understanding. So if you see, I will start from by function summary. So this gives the reads and how many requests are sent to the storage subsystem in terms of the different functions. So function means you can also take them as a metric, right, or a component, whatever it may be. Okay, so here if you see, direct path reads are the top contributor, which is almost sending 152.6 GB of reading data, and almost 94.20 seconds, almost 1.5 minutes of requests sent. Okay, so these are just informational, but still it will help you in understanding and justifying some issues. When you're justifying to the management, you need to note down all these metrics. So how much average time it is taking. Here it is just a nanosecond. So as I already mentioned, if the IO is waiting for more than 8 or 10 millisecond, right, in a modern subsystem, then obviously the storage layer is not responding properly. Okay, so here you got the total, how many reads, how many writes, and how many requests sent as part of reads, and how many requests sent as part of writes, and how much data has been flowing as part of the IO, and this is total number of waits. Okay, and yeah, this section will give you just an understanding, but when you go to the file type, right, so the table space IO, file IO, so these two sections are very important. Okay, sometimes these informations may not be present, okay, but in a production system, obviously these details will be there. Okay, so when you go to the table space IO stats, it will show which table space. So in a production system, obviously there will be multiple table spaces, so which table space is under IO contention and which data file IO will give you all the data files with their IO. Okay, so if the table space IO is having more than 20 milliseconds of wait, then obviously that is also an issue. So these are just again informational, file type summary and file type function or file type summary. It is just giving you some statistics, that's all. But when these information will be helpful when you're comparing this AWR with the baseline report, then only it will be helpful. Otherwise it is when you are just interpreting only a separate AWR report, this will not be helpful. So I will again put another baseline comparison report in the future session. So buffer pool statistics and buffer pool so buffer pool statistics is similar to the IO contention. Why? Because even in buffer cache, we know that all the data will be cached via physical reads. So server process will read all the data file blocks which is requested, and it will just put it on the buffer cache based on the most frequently used blocks, right? So pool hit percentage is 100. So obviously there is no issue with the pool hit. Okay, so if the pool hit percentage is very less, then that we need to focus on why the database is not able to catch the buffer cache properly. So sometimes if there are a lot of buffer busy waits, right? So buffer busy waits is one of the wait event, which may be one of the reason for buffer cache contention. During those times, it will be difficult for the buffer cache to maintain all the frequently used data because of the hot blocks. So if you go to this section, right, instance efficiency percentage, here also you will be able to see the buffer hit ratio, buffer hit percentage. So here if you see, it is almost 99.9. okay, so this is the same. Next comes the checkpoint activity. So even if you come to checkpoint, so when you need to check this, when you are having DBWR issue, or when you are having frequent log switch, or when you are having frequent parallel direct path writes, right? So during those times, obviously you will be seeing a lot of checkpoint writes, log checkpoint writes, and thread checkpoint writes during those time periods, or specifically parallel DMLs. Okay, so MTTR is one of the parameter that you will set for adjusting the checkpoint activity, right? So based on the value that you set on the MTR, the log switch frequency occur. So when there is frequent log switch, then obviously there will be frequent checkpoints, so which will further cause DB writer flush of data. So when DBWR frequently flush the data, there will be IO contention, right? So for DBWR should write in a regular interval, not frequently and not occasionally. So we need to understand the database and configure the settings accordingly. So next comes the advisory statistics. So this section is specifically related to sizing of the memory, memory in the sense SGA and PGA. Okay, so if you know SGA, SGA contains a lot of pool, right? Shared pool, streams pool, Java pool, buffer pool, right? So this section will give you an idea of how your buffer cache is sized, how your shared pool is sized, how your SGA is sized, and based on how many IOs or how much IOs my database SGA can be properly configured, SGA size can be properly configured. Okay, so instance recovery stats, so this will be useful whenever you are enabling MTTR, so mean time to recover. Okay, so this is completely a separate concept. Okay, so to make sure that the recovery time is faster, okay, and also there will be a frequent checkpoint, so there is a trade-off between the faster recovery time and frequent checkpoints, so that I will explain in different video. So next comes buffer pool advisory. As I already mentioned, this is just a estimation of the buffer cache size. It does not exactly give you the size. What it does is it will just estimate based on the historical catching of the data blocks, and based on that it will just recommend you the future size. Okay, so what it does is it will just increase the size factor by 0.10 for each and every row in this table. Okay, so this table contains just a size estimate. So when you increase to 64 MB, what will be the size factor, and what will be the buffers, and what will be the estimated physical reads factor, which means how many physical reads will be done when you are setting the buffer cache to 64 MB. So you can assume like that. Okay, and also the percentage of DB time for the reads. So if you set to 64 MB, almost 35% of DB time will be spent on maintaining the blocks and storing the blocks. Okay, so the moment it increase, right, the estimated DB time percentage is reduced, and the estimated physical reads are also reduced. Okay, so the main thing that you need to check is the estimated physical reads factor. Okay, so estimated physical read factor, so what is the current size? 1 is the current size. in the database for buffer cache or buffer pool. Okay, so if you see till 448 MB, the buffer cache estimated read factor is 54. So when you go down, right, so when you increase the buffer cache after 448, if you see the estimated read factor is same. Okay, irrespective of whether it can buffer the data higher than the previous rows or not, but still the estimated physical read factor and physical reads are same. So this means that irrespective of whether you increase after 448, irrespective of whether you increase the buffer cache to higher size than 448, it will not count. In the sense, it is useless. Why? Because even though if you increase the buffer cache to 512 MB, still you are getting the same benefit. If you see, the same estimated physical reads are 54. Even though you increase it to 1280, we cannot blindly say that when you increase the buffer cache to a higher size, my database will be faster. Right, so sizing the buffer cache to 448 MB and 1280 MB, both are same. It is kind of you can take any car example, right? So when you buy a Maruti car, right, irrespective of whether you so you can take petrol, irrespective of whether you take whether you put 5 liters of petrol or 10 liters of petrol, right, the speed of the car will not be increased. The speed of the car will be same. Right, unless until you upgrade the engine, the car speed will be increased. Right, but if you have only you can say 100 milliliter of petrol, at that time your car will be having some hiccups, right? So because it does not have that liquid inside, only 100 milliliter means it is very less, so it will not be able to run faster. Okay, but when you compare to 5 liter and 10 liter, it is a very high difference, right? So when you have 5 liters of petrol, it will have the same speed as 10 liter petrol. But when the car is under reservation, right, so the car fuel is under reservation, only 100 milliliter means just imagine it's just a drop of petrol. So with that drop of petrol, your car will not be able to pull the engine and pull the whole machine. So always when you are sizing the buffer cache, you just see the estimated physical reads factor. When it comes to 1, that's it. Don't increase beyond that. There will not be any benefits beyond that. Okay, but if you see any improvements after 1, if you are seeing 0.05 or 0.50, something like that, then you can increase 0.50, 0.35, something like that. And also the estimated physical reads are reduced by 30, here 25, then you can increase till 576, so something like that. So yeah, similarly we have the PG aggregate target histogram. So this is based on the historical PGA sortings. So whatever sortings happened on the database, based on that it is just recommending it. Okay, so we already seen the weight event histogram. This is similar. So we have low optimal, high optimal, total executions, optimal executions, 1 pass execution, M pass execution. Okay, so this is just a breakup of each and every sortings. Okay, so the main thing that you need to check is the one pass and m pass execution. So one pass means it is kind of reading the temporary table space. Okay, multipass means the temporary table space will be scanned multiple times. It is kind of to and fro concept. So PGA will not be having sufficient space. It will just do a one pass execution, then go to the temporary table space, come back, and again it will process the data. But in multipass, it will go up and down. First it will process in PGA, then go to temporary table space, and again go to PGA, again go to temporary table space. So it's multiple passes. So when you see some values here, then it is time to increase the PGA size. Okay, that is not good. And coming to PGA memory advisory. So this is also the same. Just check the estimated MB. So these are the size. Just check the size factor. So if you see, the current size is comes under 1. Okay, which means my PGA aggregate target is 816 MB. So for 816 MB, the work area MB processed, everything is same. If you see, even if my PGA aggregate target is less or more, the work area MBs processed are same. But you need to go and check the other columns as well to get a more understanding. If you see here, extra work area MB processed, right? So if you reduce your PGA to 48 MB, your PGA will be under trouble, because you see almost 35,146 MB processed when you reduce your PGA to 48 MB. This is just an estimation. This is not the exact processed work area size. Okay, so if you consider reducing it, it will process some the PGA size will not be efficient, and it has to do more sorting. Okay, so that too, sorting will not be done on PGA, it will be done on the temporary table space. So if you reduce it, then obviously you will get slowness during any sort operations or aggregate like group by or order by class, right? So again, you need to consider that always when you see the sizing details, it is not about increasing the size. Okay, so if you don't see any benefits at the current size, and even if you reduce the size, and if you see the same benefits, you can still reduce it. Okay, there is no harm in it. Okay, it is not always about increasing the PGA. So now here, if you see, the current size is 816 MB, but even if I set PGA to 612 MB, right, I am getting the same metrics. I am not seeing any difference. So why to waste 200 MB of PGA, right? So I would reduce it to 612 MB, and then I will just monitor it. It's not that once you reduce, everything will be under control, but once you reduce, you are telling the database that you are not having the sufficient PGA, so you need to process with 612 MB. So I'm just saving it for some other purpose. So you can, if you are reducing the PGA 200 MB of PGA, you can use it for some other purpose, like for SGA other pools, right? So you are getting the same estimated PGA catch sheet also 100, and over allocation count is 0. Estimated time are same for both 816 and 612. So here in this case, you can consider reducing it to 612 MB, but you need to monitor it, how your database is behaving. So if your database is not behaving, if you observe any difference in the work area, then obviously you need to again consider increasing it after complete monitoring. So similarly, we have short pull advisory. So every advisory concept is same. So first you see the size, then size factor. So where you see 1, that is the current size, 304 MB, and then here how many latches or library cache contentions that library cache processing that are done, right? So shared pool has library cache, obviously. So it is other caches like data dictionary cache and result cache are not that much consumed compared to library cache, because library cache is the main area where every parsing related operations happen. All the control structures and memory structures will be stored in the library cache, right? So it is also showing the estimated library cache size. Okay, so estimated library cache memory object, and how much time can be saved in parsing, estimated factor. So here also 1. So if this is the current size, even though if you increase the share pool size to a higher, you will not get any benefit. The benefits are not that much high. Here if you see, the load time is reduced from 99 to 96, but this is not giving you any much higher benefits. So unless until you get almost 80 to 90% of benefits, right? So if increasing your shared pool will give you around say 0.30 or 0.20% of estimated library cache load time, then you can consider increasing it to 624 MB. If it is just giving you like 0.2, means it is just 1 or 2% difference, that's it. From 0.99 you are just getting 0.96 benefits for loading all the objects in the library cache. So here you don't have you don't need to increase the library cache or shared pool size. So next comes the important, this is the SGA, right? So whatever you had seen previously, right, shared pool, buffer pool, all these pools are under SGA, but PGA is separate. So consider sizing the SGA properly, then obviously you don't need to individually size any other pools. So here current size is 1 GB. Okay, here also increasing the SGA, we don't see any benefits. Okay, here you can see some reduced physical reads, but yeah, it is quite less, like 100 or 150 reads are reduced, physical reads are reduced. This does not make much difference unless until you are getting more benefits, like from, if it is reducing from 53624 to 50 something like 50,000, then you can consider increasing the SGA, and also provided you need space from the operating system as well. Okay, if you don't have memory capacity from the operating system level, then there is no use. Okay, so next is streams pool, so Java pool. So unless until you are not using streams pool or Java pool, you will not get any details here, right? So when we are using export EXPDP, data pump, those kind of applications, database applications and all, our database tools, we will get streams pools advisory. Or if you are using Golden Gate or any streaming application like replication, so during those times you will get information. But currently I don't have any replication or anything. I'm just using a single instance database, so it is empty. And Java pool, so if you are using Apex or any other application related to Java, then you will get the details here. Or even if you use OEM, right? So during that time these pools will be used. So next is the buffer weight statistics. So buffer weights statistics are used specifically for buffer busy waits. So buffer busy waits are a wait event in Oracle when the hot blocks are being scanned by multiple sessions. right? So specifically you will get the class file header block, undo header, data block, and all these informations. So which block is underweight, which block is scanned multiple times. So this is just informational. So next comes the NQ activity. So NQ activity is specifically useful whenever there is NQ wait events, like NQ TX, NQ there are a lot of different NQs. Okay, so NQ is just a lock on the table. So when you are executing any DML like insert, update, delete, the table will be locked under shared lock or shared exclusive, or there are different locks, right? NQTM, and here you have all the codes. So for each and every NQ there will be a code: PS, JG, CF, DA, CR, TX, RO, SC. So unless until your top wait events come with the NQ, then you need to check. Okay, so how long this is completely an application level lock. So DBA has nothing to do with it unless until the only solution will be to kill the sessions which are locking, or you can tune the SQL statement. So next comes the undo statistics. Okay, so these are almost these statistics will be used whenever you are specifically troubleshooting any undo related issues. So for even for NQ there will be an undo, NQ undo contention or something. So there is specifically an NQ related to undo. Okay, so here it is not printed. So if you instance undo, NQ TA contention, right? So anything specific to undo, or if you are facing lot of Aura 1555 errors or lot of Aura 336 errors. So if you are not having undo space, or if you are not having the proper undo retention, if there are long running sessions, if the read consistent data is not able to get the older data, right? So expired data. So during those time you need to check these statistics. Okay, so this is the undo table space number or ID, and the max query length. What is the max time spent by a query? So it's almost 1566 seconds. So 1566 second means you can just convert it to minutes. So how long it is taking for a particular query. Okay, so next is undo segment statistics. So these are individual undo files, the each and every undo blocks. So, unless until you are focused on undo related issues, so these are just informational, you don't need much on this. So next comes the latch activity. So latching is specifically a lock on the memory. Okay, and it specifically happens in the shared pool. Okay, so even in buffer cache there are certain latches. Okay, just to protect the particular data structure or memory structure in the SGA, like shared pool or buffer cache, so that latch cannot be latch cannot be modified by any other session. So consider, so there is a memory structure or data structure in the shared pool or buffer cache. So there are two sessions. Okay, one session needs to modify this block. Okay, so what Oracle will internally do, it will just hold a latch, which means it is kind of a protection. It will just log this object, and there will be certain address, okay, address or handle given to the session 1. So unless until the session 1 completes the modification, any other session will not be able to modify this. So the session 1 will try to modify this block, but already there will be a protection on the block, which is called as the latch. So if session 2 is waiting, so if session 1 is taking 10 hours to modify the block, for example, then session 2 will be waiting on some latch wait events for 10 hours. I'm just giving you an example. Okay, so these kind of activities, obviously it will happen in the memory. Okay, so there are no 100% or perfect any perfect database where every blocks will be perfectly modified. Obviously there will be some sessions which will not be getting the enough resource, and it will take a lot of time to complete modification. And yeah, these are the different latches, as I already mentioned. So Oracle will create a cover or protective layer on top of a block, and for creating the protective layer for each and every data structure, right? So if you go to memory, there will be a lot of different data structures. There will not be only one type of data structures, right? So if you see, there are AQs. AQ means advanced queuing. So advanced queuing is specifically used for the streaming, for EXPDP, data pump, and other operations. So for data pump operations, Oracle has created a set of latches. So these are already coded internally by Oracle. So when you execute EXPDP, obviously there will be some data structures which will be internally working. Okay, the metadata, the EXPDP will be reading all the metadata in the data dictionary. And where is the data dictionary? Data dictionary is in the shared pool, right? So when EXPDP tool is running, internally these latches will be working silently, but will not be knowing in the front end, unless until we monitor and trace each and every sessions with the deeper level. We will not be knowing what happened in the back end. Likewise, we have for ASM, we have for Bloom filters, we have for a lot of latches are there. Okay, so but it is not your job to check each and every latch, like how many latches are happening. It's not the job of DBA, but you need to when there is a higher latch activity in the top foreground wait event, when latch is the problem of the database slowness, then you need to further drill down on latch, not every time. Okay, so these latches will be increased for each and every versions. So if you go back to 11G and check the latch, okay, so there is a view for checking the latch, either $V latch or something, or $V latch children or something. So there will be fewer latches in 11G. In 12C there will be more latches added. In 19C there will be further more latches added. Okay, so the major thing that you need to check is the wait time. Here you cannot go and check each and every latches and waste your time. Just check the wait time, how much time any latch is, database is waiting on any other latch, which is the highest wait time. Just focus only on that. If your problem, if your wait event problem is specific to latch, okay, not always you need to go and check this. So when I see only shared pool latch is the highest compared to other, I'm seeing 33 seconds of wait compared to other latches. Okay, and yeah, you can also check the average sleeps or miss and PCT get miss. So how many number of latch miss happened. So latching is a separate concept. Okay, so there are a lot of things to explain here. So I will explain in a deeper level on latch on a separate session. So yeah, next is a latch sleep breakdown. So this is recorded in the descending order. So shared pool is the top one. If you see the more number of get request, obviously shared pool will always be on the top, because shared pool is the one which contains all other latches, right? It is the main memory component in the SGA. So obviously there will be a lot of get requests for the memory structures on the shared pool, and obviously there will be a lot of misses. So we have latch hit and latch miss. Okay, latch hit means the session which is trying to obtain the latch gets that particular latch. Latch miss means multiple sessions will be competing for getting a particular modifying a memory structure, and the multiple sessions cannot be able to get the latch. Hence, it will just wait on CPU. It will sleep, and after some time it will try. And if it is not able to get the latch, again and again, if it is spinning on CPU or sleeping, after some time automatically that session will be marked as latch miss, because it is not able to obtain. It will not unnecessarily utilize the resource or waste the resource. So that's what mentioned in the next column. So latch sleeps. So how many sleeps were happening? So how many latches were spin on CPU? Spin gets. So after spinning some time, the session may get the latch. So how many number of sessions who got the latch after spinning for some time? Okay, so here mainly you need to check the misses and sleeps when you focus on latch specific issues. Okay, so next is also the same, but it is just a further breakdown. Okay, so if you see, previously it is giving shared pool, and next it is giving the further breakdown of each and every latches. So here only it is giving the cumulative or the total value of shared pool, but here if you see, there will be a lot of shared pool, lot of latches under the shared pool. So yeah, this is latch miss sources. So yeah, let us go to call allocation. So if you see, under call allocation itself, you are having different latch. So these are the internal Oracle call functions. Okay, so if you are aware of the call stacks, okay, if you enable trace, call stack trace for any session or any errors or anything, obviously there will be a lot of internal functions. So you should be knowing all these internal functions to understand what it is requesting. Okay, every function has an abbreviation. Okay, and if you see, most of the latches name will start with K, kernel. Okay, so you need to abbreviate all these functions to know what exactly those functions are doing. Then only you will be able to understand. Next comes a mutex. So mutex is also similar to a latch, but it works in a different way. So Oracle had introduced mutex later because of some drawbacks in the latches. So mutex were introduced, and when mutex are used, the algorithm itself is designed in such a way that it will be faster compared to a latch. But even in mutex, there are a lot of other trade-offs. Okay, so yeah, even for mutex, it is a complete concept, so I will explain it separately. So if you see, cursor pin is the one which is having a lot of sleeps and wait times, but our issue is not related to latch here, right? So our issue is related to CPU, resource manager using high CPU. So next comes the segment statistics. So segment statistics are the section which is specifically related to IO, like tablespace IO statistics or IO stats. Okay, so if you want to identify the segments related to for which segment is having the high reads, let it be a logical read or physical read. Okay, so logical read means the blocks are read from the from the data file, right, and it is put on the buffer cache, and then the session will read it from the buffer cache. So physical read means it is completely the server process will read from the data file. Okay, so logical read means it is just reading from the buffer cache directly from the memory. So if you see which segments are read from the buffer cache or memory, so you can easily identify like which segment has the highest logical read and what is the percentage of time spent on this current AWR snapshot duration, right? And with that you can further drill down, like if there are any fragmentation issues, right? So you can just run a segment advisor. So there is an advisor specifically for segment, so it will just give some recommendations like partitioning the segment, right? So if the table size is very big and if there are a lot of physical reads, then partitioning may be the solution to reduce the IOs. Also, other issue will be fragmentation. Other issue will be creating an index. So there are a lot of other use cases. So likewise, how we are checking logical reads, we are checking the physical reads, which means directly reading from the data file. Okay, so next is the physical read requests. So how many IO requests were given to the disk? Okay, so this is the actual read which are completed, but these are the read requests. Okay, it may be completely satisfied, the completely the physical read requests will be sent, but we cannot say that all the read requests will be fulfilled. Okay, so few of the physical reads may or may not be. So in such cases where there is a physical read and suddenly database is requesting this many number of physical reads and suddenly database got hang or database got down. So during those times you cannot say that that physical read is complete or fulfilled, right? So in between the database got crashed, so obviously the physical read may not be successful. So these are the unoptimized reads. Okay, unoptimized read means these are direct path reads, which means sorting or aggregation. Segment by physical direct physical read. So these are also direct path reads, aggregation or sorting we can say. So when we are using parallel, obviously a lot of direct path reads will happen. And again, we just created this test case for testing the resource manager, right? So we have two different owners, app low and app high, and we are just doing a CPU test. So yeah, for differentiating the resource manager, I have just created two different resource groups and executed the test case. Okay, so next comes the writes. So similar to how we are focusing on the physical reads, if the majority of the issues related to writes, then you may need to check this, which object is going through more writes. And segments by data block changes. So these are specifically related to the redos. So if multiple modifications happen, obviously redo log generations will be high. Okay, so these segments were modified frequently, but these are not application tables. These are internal tables related to sysocs, okay, and related to statistics. And these sections are also important. So if there are any row log weights, if there are any NQs, then you will get information on this, which table is going through a lot of NQs, and ITL weights, interested transaction list weights. So these are specifically related to either the segment level issues like the PCT free settings and the init trans. Okay, so again, this is a complete separate concept. And coming to buffer busy wait, so we already know if there is a buffer contention, there will be buffer busy waits. Okay, so similarly, yeah, we have dictionary catch stats. Okay, so this is also a separate concept where whenever you are getting row catch contention, so row catch contention is a separate wait event. Okay, you will get lot of row catch locks whenever you are doing rigorous DDL changes. Okay, so during that time there are different categories which are divided by Oracle. So for each and every category, so when you are granting something, object grants, during that time if there are any issues, then you will get row lock contention. If there are a lot of modification requests for histogram, then you will get row lock contention. So let us see a separate session video on this. Again, library cache activity. So library cache activity is also specifically related to DDL changes. So when there are any compilation of objects or modification of the objects, definitely there will be pin requests, right? When you are using any alter table, modify column or something like that, then you will get pin requests, and there will also be reloads and invalidations, right? So when you are modifying a package, existing package, you need to again recompile it. So if you are not recompiling it, then it will become an invalid object, so you need to again compile it. So there is a separate, again, it is a ocean, right? Library cache activity. So for each and every category there will be issues. So when you are specifically doing any audit related modifications, audit related issues happen. When you are specifically creating multiple DB links, and if there is a contention in the library cache for DB links, then you will get DB link library cache issues. So most commonly you will get issues with the SQL area, because the SQL statements are the one which will be the majority, executing majority of the consuming majority of the database time. Okay, so next comes the memory statistics. So memory statistics, this is similar to the sizing, memory sizing. This is just a breakup of all the pools in the memory. Okay, so here the main thing that you need to check is which pool is growing. So you need to monitor this as well. So which pool is dynamically growing, and if you see, this last column is very important. So here if you see, Oracle has given a lot of short forms. So STA stands for static. Okay, so if you see, almost majority of the pool are in static size, it has not dynamically increased. Okay, and if you see, there are two rows which are showing shrink, here growth, and deferred. So you need to mainly focus on shrinking and growing. Here, since most of the databases today in today's environments will be using ASMM, automatic shared memory management, right? So AMM will only be suitable for small databases, and manual memory management will be will not be efficient, right? Every time any DBA cannot come during midnight, and he cannot monitor the SGA sizes. So both of these are useless. Okay, we cannot say that a database will always be small, right? So small means it's kind of a very small database. Okay, so only up to a few memory size AMM can support. So ASMM is the majority, almost 99% are using ASMM. So here default buffer cache size is shrink and shared pool size has grown. So internally Oracle will use some algorithm to resize every pools. So if it does not have size available, what it will do, it will shrink the space from any existing pools based on the usage. So here buffer cache was not in highly demand for during this time, so that's the reason it has decreased the buffer cache size from 656 to 640, and it has increased the shared pool size to 288 to 304. Right, so likewise it just exchange the size, reducing on one side and increasing on another side. So here if you see any significant growth in the memory pools or shrink in the memory pools, you need to go and check the advisory, the previous section that we seen, right, memory advisory section, and check what size can be used or increased. Okay, so next is a process memory summary. So this is specific to the process, so which database and which specific process is consuming more memory. Okay, either PL SQL or SQL or other, and how much memory can are freeable, right? So you can get an idea on this. Yeah, so next is SGA memory summary and SGA breakdown by pool. So these are just informational. Okay, next is the replication statistics. So when you are using Golden Gate or streams, you will get all these sections enabled. Next one is the distributed server or shared server. So if your database is a shared server, obviously these sections will be used. Okay, so most of them will be dedicated. Okay, dedicated servers. And next comes the init.ora parameter. So if you want to check the parameters, what are all the parameters enabled on the database, you can check this. So this is specifically useful when you are troubleshooting or diagnosing remote issues. Okay, so when you are diagnosing any customer issues, right? So customer will share only the AWR report. He will not give you direct access to the database. So or the server. So you will not be able to check the P files and all. Right. So in the AWR report itself, if these details are printed, then you can check all these details remotely. So like what is the memory size, what are all the number of processes, what is the resource manager plan, right? So everything you can check. Next is the parameter modification. So if you want to know whether any parameters were modified during this time, so as I already mentioned, we just used a test case to check the resource manager. So we have created a resource manager plan. So this parameter was modified during the snapshots when this AWR report was generated. So this is also one of the hint, right? I can easily identify and understand that during this time something related to resource manager was modified. So I need to focus on the CPU and configuring the right plan for the resource manager. So next is the control file. So these are informational. Okay, so yeah, so that's it about the AWR. So next comes the ASH active session history report. Okay, so in the older versions like 11G or 10G, you will not be getting the complete AWR report with the active session history, but in latest versions Oracle has included both active session history and ADDM report on the AWR report itself. Okay, so you don't need to separately generate the ASH and ADDM because of time constraint. So you can just generate only the AWR and just get the ASH details as well. But if you want more specific information related to the number of samples, then you need to generate a separate ASH report. So I also would have mentioned in another video where the purpose of using different reports like AWR, ASH and ADDM. So you can go and check those videos for understanding why you are generating AWR or why you are generating ASH, right? So when the issue is happening for out of 1 hour, if the issue or any hang happened for 1 minute, in between the 1 hour, then you can go for an ash report. So that will give you more detailed information because samples will be collected. So AWR is completely time based and ash is related to sample based. So I will add this on the description video as well on the use cases of different reports. Okay, so hope you like this video. So we'll see a different scenario related to AWR in the another session.